Thanks a lot for having me in this seminar. I hope you can see my slides. I hope you can hear me well. I'm happy to be interrupted. So also my talk in a to a significant extent, my talk will be simplified by some of the content which was already announced by Evgeny, which I'll just skip through very fast. So yeah. In a sense, I would like to say that we just heard a talk which was more on scalar curvature, and now we'll hear a talk on the not only part from the title of the seminar. So I don't really have much to say about scalar curvature, but I'll talk about some inspirations coming from scalar curvature. And those inspirations will lead me to some of the some questions that I worked on. So in particular, I would like to talk about my joint work with Sasha Bernikov. So we'll get to that after I very briefly go through some of the preliminary parts. So let me say again that there is this notion of the Urysohn width, which can be defined for a general metric space. And the d-dimensional width is supposed to measure how well you can approximate your space with a d-dimensional simplicial complex. So more rigorously, let's say that the Urysohn width in degree d of your space X is at most W if you can map your metric space to something at most d-dimensional, a simplicial complex of the dimension most d, such that the diameters of all preimages of all points, I'll be calling them fibers, such that the diameters of all fibers do not exceed W. And the diameters here, once again, are measured in the extrinsic metric of the space X. So generally, I do not assume some connectivity properties. So yeah, here's in the right you can see a picture which you could keep in mind. So it's supposed to picture the one-dimensional width of the two-dimensional normal Euclidean square, purple in this picture. So if I map it to a one-dimensional space, to a graph, then the fibers are certain subsets of my space X, and you can just think of certain like foliation in quotes of your space X or slicing in quotes. So I might casually use those words, meaning that yeah. So essentially, what's happening is that my space X is represented as a union of a of a like one-dimensional family of certain fibers, and I measure the diameters of those fibers. If all of them have diameter at most W, then the Urysohn width is at most W. Then I try to come up with the most efficient map to a one-dimensional complex in this picture. So I consider infimum over all maps P as in this definition, and like the least possible W or the infimum of all those W will be by definition the Urysohn width. Here's the photo of Pavel Urysohn. He suggested this definition in the context of dimension theory around 1923. The next year he died, and this definition is now contained in a paper which was published by his friend posthumously, yeah, based on some drafts of Pavel Urysohn. So yeah, once again, here is this definition. Yeah, so I consider all maps to lower dimensional simplicial complexes. For each of them, I consider the maximal diameter of a fiber, and for then I minimize over all continuous maps P. This is what the width is. Let me briefly mention some trivial properties of the width. It's monotone in dimension. So the zero width is basically the diameter of the space or the maximal diameter of a connected component of the space. yeah, one-dimensional width corresponds to how well you can approximate your space with a graph. Uh, this width will be, of course, smaller than the diameter, etc., etc. So yeah, and d-dimensional width being zero happens if and only if when the covering topological dimension of your space is at most d. And yeah, I wanted to mention also monotonicity in X. So if you have one metric space is an isometric subset of another one, then the widths are monotone in the obvious way. So I've formulated in a bit more general way, but it's pretty much obvious. Okay, so and I also wanted to mention that, yeah, how you might think of this if you have a non-compact space or manifold, Riemannian manifold, you might think of this width as a way of measuring the macroscopic dimension of your space. You just zoom out far enough so that you no longer see the details on, some finite scale. And this way you can define the macroscopic dimension as the minimal dimension d such that the d width is finite. So yeah, my excuse to talk about this in the seminar on scalar curvature is that there are a bunch of conjectures, mostly due to Misha Gromov, maybe some of them also stated by Shen and Yao. They were also mentioned by Evgeny. So the strongest one, or one of the strongest one, says that positive scalar curvature implies the an upper bound on the codimension 2 width of your Riemannian manifold. So in a weaker version, which is still open, a positive scalar curvature implies a bound on the codimension 1 width. So it's pretty much the same as to say it's pretty much the same as to say that macroscopic dimension of the universal cover of a manifold drops by 1 in the presence of positive scalar curvature. And the even weaker version, which is still open, which is also mentioned by Evgeny, is that positive scalar curvature implies that the manifold cannot be aspherical. So it has some non-trivial homotopy group in degree 2 or higher. So yeah. For example, the first conjecture is only known, the strongest one is only known in dimension 3. The last one is known in dimensions 3, 4, 5. And in dimension 2, everything is obvious, more or less. Okay, so another piece of motivation for me is that so scalar curvature, since it's hard to study, can be interpreted metaphorically in a few ways. So this one was also mentioned by Evgeny, that scalar curvature is basically positive scalar curvature responds to certain behavior of the volumetric behavior of small balls, the balls of small radius in your manifold. So metaphorically, positive scalar curvature can be compared to this condition in the box, which says that, yeah. So that's what Evgeny called macroscopic positive scalar curvature. It says that if my unit balls all have metric balls of radius 1, I call them unit balls in my manifold. If they all have small volumes, less than a certain small constant, dimensional constant specify in advance, then so we can talk about positive macroscopic scalar curvature. Yeah, it's not the same as positive scalar curvature, but some of the facts which are known for macroscopic positive scalar curvature correspond to the conjectures that we've seen before. So yeah, so this was mentioned as well. A theorem of Larry Guth that says that macroscopic positive scalar curvature actually implies an upper bound on the codimension 1 width of manifold. which is a macroscopic version of one of the conjectures that I stated before. Uh, though it does not imply the same assumption, does not imply it's not enough to assume that volume are balls, unit balls are small. It's not enough to assume that in order to conclude an upper bound, a bound from above for the codimension 2 width. So I stated here is the question. So maybe we want to require some stronger assumptions. So in order to get the microscopic analog of the strongest conjecture. Yeah, this is something, this piece of work, we have a little result with Han Albert and Larry Guth, which was also mentioned by Evgeny, which is basically mentioned by this old work of Gromov Lawson, which says, among many other things, it just observes that on a three-dimensional manifold with scalar curvature at least one everywhere, it happens that every null homologous one cycle bounds in its neighborhood of controlled size. So it happens that if you start with a one cycle and you know that it bounds, that it can be filled by two surface with boundary, then you also know that you shouldn't look for the surface far away from your one cycle. You can just look in a neighborhood of certain very explicit size, reasonably small, and you'll find it there. So this motivates my second kind of metaphor or observation that positive scalar curvature can also be compared to this condition. Every null homologous one cycle bounds in its small neighborhood. Small meaning like, some explicit size. And then the question from the previous slide can be resolved in affirmative, but with many additional assumptions, only in dimension 3. So roughly speaking, you can just take another definition of macroscopic scalar curvature. You can say that positive macroscopic scalar curvature amounts to two conditions as opposed to just one. So it's just not just balls of certain radius have small volume, but it's also this geometric contractibility type of condition on loops. Again, this condition, which I stated here, every loop of length at most something bounds in its small neighborhood. It's sort of motivated by this thing in the frame. There is no null homologous assumption there, unfortunately, so we have to pay for this, go into the macroscopic world by something. But that's the result we were able to get. Yes, it was mentioned by Evgeny in the context of an idea which shows up in the proof. Thankfully, Evgeny actually explained it, and I'm not going to do this because I want to skip to some other facts that were not mentioned in the previous talk. So one of them is that, okay, so the metaphor that I gave in the previous slide, the metaphor that this condition, that PSC can be compared to this condition, non-homologous cycles bound within reasonable distance from its name or from the cycle itself. This analogy shouldn't be taken very seriously because of this example, which I know from Sasha Bernikov, but then later I found it in Pendragon's work from 1930. It basically says that, okay, if we are hoping that this condition in the box, null homologous cycles bound in the small neighborhood, if we hope that they imply the same thing that conjectural positive scalar curvature implies, namely some bounds on the Urysohn width, then this is not the case. So let me briefly explain this example. So you start with, let's say, normal unit square in the Euclidean plane. you punch many holes in the square, and then to each hole you attach a cross cap. Or in other words, you cut out small disks and then you glue the boundary, every piece of the boundary to itself using a map which winds around twice. It's the same as to say attach, connect some with RP2 or attach a cross cap. So this space is, well, okay, if I started with a sphere instead of a square, I would say that this is just a connect sum of many copies of RP2 with a certain metric. So it doesn't matter which metric you, well, let's just take small model cross cap and attach them to each hole there. So you get the metrics, you'll actually get a two-dimensional non-orientable manifold. And it's easy to show that it cannot be approximated by a one-dimensional graph. So it's Urysohn dimension one Urysohn width is not small. It's approximately the same size as the original square or original sphere. But thanks to those RP2s, the metaphorical macroscopic curvature condition is satisfied. So every non-homologous one cycle with z coefficients does bound in its small neighborhood. Small means like size between, like I put those RP2s on a very fine grid, and there is the side length parameter of this grid, and this is what small means here. Yeah, so that's just a cute example. You might ask what happened with other coefficients.
Sorry, Alexey, I have a quick question. So you're saying that every non-homologous one cycle bounds in small neighborhoods. So what would be an example of X with this property that also has large? It's a two-dimensional X, right?
Yes. Yes, you want to ask me about dimension 3, right?
No. So it's a two-dimensional disk, and it has very large Urysohn width, but every cycle can be filled in a small.
As long as it already fills in this manifold, it can be filled in a small neighborhood. Yes. So for
I
example,
see. Also, you define X as RP2. I thought you're attaching all this RP2 to something like to some other space.
okay, so let me just maybe repeat again. So I start with a square. I cut a bunch of small holes.
How large is the square? Is the square very large?
The original square is large, and it's responsible for this Urysohn one width.
Okay, I see. Okay, now I understand. Thank you.
Okay. So yeah, the point is that for example, if you in this picture, if you take a loop which goes around some of those RP2s, this loop does not bound with z coefficients. So the only loops that bound look like, oops, sorry, look like this, and they can be filled in small neighborhood. Yeah, you might ask me what happens with other coefficients. Then Panchardin actually gives examples. Like instead of attaching cross caps, you might do like a little bit. You might glue each circle of the boundary of a cutout disk to itself using a map which winds around more than 2 times. And you'll get counterexamples for every given coefficients. They're not manifolds anymore, but you'll get counterexamples for every given coefficient. But it's not clear what happens if you require this condition in the box to be true with all coefficients simultaneously. So this is very much not clear to me. Okay, so and one last link, which will be the most to scalar curvature, will be the most vague one. So I basically drew this slide from some slides of Hannah Alpert. And I oversimplified them even further. So maybe this is not literally correct what I'm saying, but Okay, there was this very outstanding work which proves that spherical manifolds of dimension 4 and 5 cannot carry a metric of positive scalar curvature. And an oversimplified sketch of the proof, oversimplified to the extent that it may be not correct, but let me still say a few words, goes as follows. So for dimension 5, you work in the universal cover, which is contractible, or like because you start with an spherical manifold, you assume that it carries positive scalar curvature, and you go to the universal cover, you find there an infinite geodesic line, you find some kind of like transversal hypersurface to that line, which intersected once. It's a hypersurface also minimal, so that it inherits sort of some kind of PSC property, in a sense, after a conformal change, perhaps. Then this is what this blue disk in the middle is supposed to represent. That's a four-dimensional minimal hypersurface. Then you step away far inside this hypersurface. You step away far from the only intersection point to go far. You consider a certain bubble or whatever inside this surface. It has certain boundary dn, which is first far from the geodesic line we started with. And second, it also inherits some PSC properties because of the properties of mu bubbles. And then you hope to show that this dn boundary of n is actually fillable nearby, like within the neighborhood of this boundary, which doesn't meet the geodesic line. And then this will lead to a contradiction because it has to have the same algebraic intersection number with the line, but it does not. Yeah, so in lower dimensions, this part to show that something feels nearby was just by saying that, okay, like if we knew that the diameter of this boundary of n is small, then we've just used the geometric contractibility properties of this universal cover and finish immediately. But here we can say this, so there is some very clever and tricky procedure of slicing and dicing this boundary in chunks of small diameter, and some like which also meet each other in a controlled way, which leads eventually to showing that like you still can feel this boundary fan nearby. Yeah, but for me, in my vague and oversimplified sketch, it's only important that some like a property having to do with width, which is crucial in this argument, is that this boundary fan can be shown to have a small one width, as long as it can be sliced in chunks which have small diameter, and their intersections also, they meet each other in a controlled way. The intersections also have small diameter or something like this. So allegedly, the same argument doesn't really prove that this conjecture in dimension 6. From what I understood, it could be viewed as a reason that you cannot do the same argument in dimension 6 because you can still go to this boundary of n, which will be 4-dimensional, and you can try to do some slice and dice, and the chunks will have small one Urysohn width, but you cannot conclude that the whole delta n, the n has small Urysohn 2 width, for example. So this is actually, finally, I'm getting to what I want to make the main topic of my presentation. So in that sketch, one property which was needed for the proof, but it failed in higher dimensions, was well, basically, a crucial property was to just understand the behavior in this type of question. So I formulate as a prototype question here. Suppose you start with a certain space, which is already sliced or diced or foliated or in some other way, like represented as a union of simpler chunks. So I would like to stick to this formulation. So suppose it's foliated in quotes by an m-dimensional family of n minus m-dimensional sets. And so when I say foliated, I don't mean anything honestly. So I don't require any regularity of those sets, except maybe their dimension is n minus m. But honestly, in the results, I don't even assume that. So, and assume that I know something about let's say, the supremal width on a certain dimension of those leaves of the foliation. Does it imply something about the width of the whole space? So that's the modal question. And I'm gonna survey a few variations on this question in the remaining time. So maybe like to formulate even a simpler instance, which is already very non-trivial and already useful for some applications, would be useful if the answer was yes to this question. So let's say that your topological ball of dimension n is foliated, sliced in a one-dimensional family of things, sets of dimension n minus 1. Can you guarantee that they at least one of those fibers has dimension n minus 1 in an essential way so that it cannot be approximated by something lower dimensional? So even in the case when I start with a usual Euclidean unit cube and I slice it with using some one-dimensional family of n minus one-dimensional entities, this is very much not clear, but I'm gonna explain in the sequel what happens. I formulated the question because the answers will be mostly no, sometimes yes under additional assumptions, but this is the main question. And I hope I motivated it enough if it was not already interesting on its own. So I call it a waste type of question because in other words, what I'm saying is I have a n-dimensional space, I map it to something lower dimensional, and then I want to guarantee the existence of a fiber large in certain sense. And here, this certain sense will be by measuring widths of the fibers. But generally, people were interested, investigated many different questions which fall in this setting. Okay, so maybe another bit of motivation, if that was what I said was not enough for you, another bit of motivation is that the Urysohn width measures the approximate dimension. Like it measures how well, if the width is small, it says that your space is approximately d-dimensional, in quotes. And for the usual dimension, not the approximate, but the usual topological dimension, we do have and sort of, very intuitive waist type of property. So if you slice your space of certain topological dimension by an m-dimensional family of leaves, then at least one of those leaves will have dimension, which is like the dimension of the original space minus m, which is very intuitive, exactly what you expect. And then the question that I formulated in the previous slide is basically like, is this result robust if I replace the dimension with approximate dimension? And again, by the approximate dimension, I mean, like also everything is metaphorical in quotes here. So let's say that something is approximately d-dimensional if its d width is small. So, okay, so from the very beginning, the answer is no. And the example, very nice example, which could be called the mother of examples, because most counterexamples in this field just come from this one. It appeared in a paper of Gromov. Uh, so let me let's like leave it here for a second. Here I just reiterate that, okay, the general ways type of question is like you have a map drop in dimension and you ask, is there a fiber? Can you always guarantee the existence of a fiber of decent size? And this example of Gromov basically says, well, okay, if your measure size with the Urysohn width and you expect it to be, behave like the dimension behave, then the answer is no. Well, with different measures of size, that just to one random fact about perhaps more famous waist estimates, then yeah, with different measures of size, the answer is oftentimes yes. And so, yeah, those proofs though are very, very, very involved. So yeah, if you measure the volume of fibers, then there are several celebrated theorems, many of which are due to Gromov, uh, which say yes, there is always a fiber of large volume. Yeah, I just cited one particular result which actually follows from Gromov's waist of Gaussian measure theorem. Um, but yeah, just to have some idea how those compare in a simple case when you have a 3-cube sliced with a one-dimensional family of surfaces. So let me, since I said this question, this example of Gromov is very important and appears everywhere, let me briefly explain it to you. So first, think of this unit cube as actually maybe we'll rescale everything. So the unit cube will become a huge, huge, huge cube in R3. And in the same R3 where my huge cube lies, I will consider two cubical grids. One of them which will be, I will only draw like one cell of one of the grids. So if I consider the unit cubical grid and I draw it in blue, in the picture you see just one cube from this cubical grid, its unit size, for example. And then I also drew the dual cubical grid and I drew it in red. So it's the one-dimensional skeleton of that grid is the red. So you should, in your head, you should translate this picture by a lattice, by Z3, by the lattice and into a lattice, and imagine, the periodic picture. But I only draw what happens inside the unit cube. Okay, so I want to slice everything by one-dimensional family of surfaces of small one width. That's my goal to show this proposition. And in order for here's the map. So f of x is the function which sends every point in my ambient R3 to the interval 0, 1. So it just measures two distances from your point x in R3 from the red skeleton, one-dimensional skeleton, into the blue skeleton, and normalizes the distance to the blue skeleton, let's say, so that it becomes a number between 0 and 1. Then a generic fiber of this function will look like this, the purple surface. It's not smooth. Everything can be made smooth if you want, but it's not important. So yeah, this purple surface is a image of a generic number between 0 and 1, where distances were measured in L infinity for this particular picture. But again, it doesn't matter in general. But yeah, then you should think that this purple surface is replicated, translated by the lattice Z3, and you get a huge tubular surface in R3. And it's sort of obvious that this purple surface is actually approximately one-dimensional because it can be mapped, for example, to the red skeleton, or it can also be mapped to the blue skeleton in an evident way. And in either way, you'll get fibers small. You'll get fibers, of size, less than 10 or something. And this gives you a foliation of a huge cube in R3 by surfaces. Most of them are like normal surfaces. There are two degenerate ones, which are exactly the fiber over 0 and the fiber over 1, the red skeleton and the blue skeleton. And each of those surfaces is approximately one-dimensional, but this might be a little bit counterintuitive because I sliced the three-dimensional space into a one-dimensional family of surfaces, and for some reason they're all approximately one-dimensional. So the dimensions don't add up as they should, as they're expected. Okay, so more generally, what can be shown is that if I'm more modest and I measure the size with, like, here I have something which behaves like n minus m width. In order to make this statement true, in order to make the answer to this question yes, I'll have to replace n minus m with n over m. This is the optimal parameter of which can be placed there. So, yeah, the fact that the positive result in this direction is also actually it's a small and pretty trivial proposition from the same paper of Gromov. Yeah, here maybe there are too many parameters, but yeah, basically it says that if you have a space of dimension which approximately behaves like a product of two numbers m and d, and you map the space to something m-dimensional, then there is a fiber of large d width, something like this. And as I said, like, yeah, the proof is really, really easy, simple. Basically from some equivalent reformulation of the definition in terms of coverings. And as I said, this proposition cannot be improved. I haven't found this written down anywhere, so I wrote it down myself. And it just says, yeah, so if you just, shift this dimension parameter by 1, the proposition is no longer true. So you can map, and this is a very fun fact. I find it very fun. You can map R to the n, where n is approximately m times d, to an m-dimensional simplicial complex, in fact, just a simplex, so that all fibers have small d width. So this is just an amplification of Gromov's example from the previous slide for in the whole range of dimensions. So maybe let me say just one word about the proof of this. So this is like similarly how we started from two dual scalata in R3 in order to come up with that counterexample in the previous slide. For example, the next non-trivial case will be dimension 5. You start with R5. In R5, you can find three, in a certain sense, dual. I don't know how to say dual, so that it applies to three entities. Three one-dimensional scalata in R5, such that similarly to the Gromov example, you can interpolate between those three one-dimensional scalata, and you'll get a two-dimensional family of three-dimensional surfaces inside R5. So between every two scalata, you can interpolate the same way as before. But in order to fill in the whole R5, something a little bit more tricky will happen there. But it happens that it can be done, and each three-dimensional surface will be mapped naturally to at least one of those three one-dimensional scalata. So yeah, this can be done. There are very explicit and neat constructions. I guess I don't want to say more about this because I want to sketch more neat proofs, which I like and which I think deserve to be better known. So here is an application of the same proposition of Gromov. Application is a theorem from topological combinatorics, and it says, so it doesn't have to do with any kind of metric whatsoever. So it's a, yeah, it's a combinatorial proposition, which says if you have an n-dimensional simplex of large dimension, which also behaves roughly like the product of two numbers m and r, and if you have a continuous map dropping dimension to m, then there is a fiber which is sufficiently large in the sense that it will have to intersect all faces of dimension, which are like almost complete, almost n. Also behave like a product. Yeah, well, why would you be interested to know this theorem? Well, maybe I can also say a few words about this. So one interesting thing that it does generalize several known results from classical combinatorics or like very classical, like there are some statements, combinatorial type of statements equivalent to the Brouwer fixed point theorem. So this generalizes them. This generalizes the Rado center point theorem from some convexity. It also, and the method of the proof, like there are several proofs of the result. I want to briefly sketch one, which is the simplest in my opinion, but there are also other proofs which happen to be of interest in some other fields as well. So allegedly, this theorem can also be proven by certain Gromov's method of ideal valued measures. And this also has applications in other branches of geometry. So I heard, like, I listened to a talk of Leonid Poltorovich, and he was explaining how to uh, use that method to prove some existence of non-displaceable fibers in symplectic manifolds or something like that. So yeah, this stuff is can be generalized to other things where you don't expect to see that. I just reformulated this theorem, and I wanted to give you a quick glimpse into the proof. The proof goes as follows. So assume that, so no, this is a very simple case. I have a two-dimensional simplex, and I assume that no fiber of a map to one-dimensional graph, no fiber meets all three sides of the triangle. So an orange curve is an example of a fiber. Since it doesn't meet one of the sides, it can be naturally projected to the opposite vertex. And then what you do is that you put the simplex in Rn and in a sort of nice position so that you can reflect it and tessellate the whole Rn with the reflected copies of this simplex. And you draw this type of kaleidoscopic picture on the right, on the right. And then it just happens that now this, this extended orange fiber, after all the reflections, it has a small zero width in this particular picture. In general, we'll have a sort of small width of certain dimension because it can be projected as in the picture on the left to certain sub-simplex of my simplex. And it happens that I managed to foliate the whole Rn, foliate with leaves. Each of them has a small width in a certain dimension. But according to Gromov's proposition, this is actually not possible. So yeah, once again, the sketch is that you assume the contrary. You amplify this counterexample, which you like this, which you started with, by using a sort of nice triangulation of Rn. Then you use Gromov's proposition on waist measured by widths, and you get a contradiction from there. Basically, it tells you that Rn then has to have width like microscopic dimension less than n, which is not true. Okay, good. I have, I guess, 15 minutes right? Is that right? Then I want to sketch a few more results in the same direction. So in Gromov's example, the mother of examples, Gromov's example, you can argue, okay, all the purple surfaces in that picture, they were topologically complicated. They had a huge fundamental group. Maybe something can be said if you restrict, if you have some additional assumptions about your fibers, your leaves of your foliation or something. Maybe you know in advance that they have simple topology. Can you say something in that case as well? Okay, so this is a partial yes answer. So yeah, which should be compared to the mother of examples. Yeah, from now on, everything is from joint work with Sasha Bernikov. And yeah, so here is the baby case of our theorem there. It says that if you have a three-dimension, well, yeah, basically the same result if you additionally assume that your fibers are just disks, the same result, the prototype question can be answered in the affirmative with sort of non-sharp bounds on the width. I have some pictures to show how the proof works for this specific case. So in this picture, I have my three-dimensional cube, and I maybe, after some homomorphic change or whatever, like I just think that my map to 0, 1 is just the projection map. So my fibers, which were homomorphic to disks, are now vertical in this picture. And each of them, assuming the contrary, each of them has small one width. Let's prove then the whole cube will have an upper bound on the width, which will contradict, the obvious bound that we started with the cube, which had a certain two-dimensional width. Sorry, I think I confused myself and I said one width instead of two width. Once again, here's the essence of this result. I started with a 3 cube, which is already foliated, sliced by vertical squares. I know that the metric on this cube is somewhat weird, and it makes every vertical square have small one width. So every vertical square is approximately one-dimensional. And I want to use this information to show that the whole cube is it can be approximated well by two-dimensional space. And this will give me my contradiction. So the trick here is that, okay, so if like my foliations in each separate vertical square are not aligned with each other. There's some foliations, but I want to make them agree with each other. So each vertical square is already mapped to a certain graph, but I want to make this map to a graph, somewhat continuous with respect to this one-dimensional parameter which I have in this picture. So in order to do this, the crucial idea is that I start with two close squares close to each other. They have certain slicings which are not related to each other, but I want to relate them. And I want to interpolate between two slicings. If I'm able to do that, I'll be able to glue all those maps. So my goal is that to come up with a foliation, with a map from the whole cube to a two-dimensional space with small fibers. So hopefully I'll manage to do this. The key lemma here is this interpolation between slicings thing. So here's how it works. I'll just show by picture. So I start with this red slicing, and I want to arrive at the green slicing. They don't look alike. So okay, so now I start a certain continuous process, which starts from the green slicing and will finish with the red slicing. And yeah, so basically, uh, the red slicing just takes over the whole square in the process. So this is sort of step, I don't know, after time 0.2. This is how it looks after time 0.4 or something like that. This is how it looks time, I don't know, 0.6 or something. And eventually the red slicing just takes over and replaces everything. And now this is a continuous family of foliation. So each of those pictures should be read as follows. So for example, here, uh, it might be a little bit deceiving. So let me explain. So I had this fiber of the red slicing, but it also meets many fibers of the green slicing. They will be merged together. So everything that touches this frontier, the red frontier, will be merged to the same fiber of the new map. So in this intermediate step, this whole orange area will be considered as one fiber because otherwise it doesn't make, there's no other reasonable way to interpret this picture as a slicing by one-dimensional family of things. It's no longer one dimension, but it doesn't matter. The proof works. So in this way, every picture can be interpreted as a slicing. And now all those slicings can depend continuously on my one-dimensional parameter. And you can glue everything together. And you can, so assuming that, all your original slicings of each square had leaves of diameter at least less than 1/3, you can show that in the final family of slicings, continuous slicings, each fiber will have diameter less than 1, right? So for example, in this picture, I had this fiber of diameter less than 1/3, but I also knew that, for example, if I want to measure distance between 2 points, X and Y here, I also knew that this fiber of the green slicing was diameter less than 1/3, and this fiber of the green slicing was diameter less than 1/3. Now the merged fiber will have diameter less than 1. The distance between X and Y will be less than 1. And therefore, I managed to slice my whole three-dimensional cube by a two-dimensional family of leaves, each of them having diameter 1. But this is impossible because the original three-dimensional cube had two width exactly 1. So that's the sketch of the proof. There are more details there, and but basically this conveys the idea of this baby case, which I wrote here in pink. And I just formulated the more general theorem of which this was a baby case. It's not much more general than this baby case, and it has some additional complications. Yeah, so here we assume that fibers have bounded topological complexity. Their like first beta number is bounded by a certain number beta, and this beta participate in the answer. So you guarantee that there is a fiber, your map drop dimension by 2, and there is a fiber of Urysohn with at least something, which also depends on this beta. Nothing is sharp, of course, but this is still something. Okay, so basically, if the original mother of examples seemed counterintuitive to you, then this pink statement was one way to save this intuition by assuming additional topological assumptions. It turns out in general that even topological assumption of like all fibers being trivial topologically does not save the situation. And this is a cool example, which I still want to sketch in the remaining 5 minutes. But that's going to be the last thing I'm going to be talking about. So Yeah, super awesome example by Sasha Bernikov. It says that there is some weird Riemannian metric on the four-dimensional cube, such that if you slice it with vertical three cubes, each slice will be approximately two-dimensional, but the whole thing will be essentially uh, four-dimensional. So I didn't write it here, but metric, this metric with UV3 large, UW3 large. Yeah. Here's an attempt to explain this result. It has an intuition coming from the mother for all examples. So in this picture, I have my four cubes sliced in a one-dimensional family of three cubes. We start from the standard metric on the four cube, and now I'm going to explain to you how to modify this metric in order to get this example. So my three cubes in this picture are parameterized by parameter t from 0 to 1. So in the three cube parameterized by number t, let's draw the surface from the mother of examples. Let's draw that, like for t equals 0, we'll draw the red one-dimensional cubic skeleton in our cube with very, very, very fine grid. So I only draw one cell here, but think of a very fine red one-dimensional cubical grid in this three cube on the left. When t equals 1, it will be the dual blue one-dimensional skeleton, as in the mother of examples. And for generic parameter t in between, it will be that purple surface from that example. So in each three-dimensional cube here, I have a distinguished surface. And now what I do the following. I say, okay, so for now, each three cube had the usual Euclidean metric, but I'm gonna modify it in the following way. I blow up the metric in the direction normal to this distinguished surface sigma, different for each cube. So it becomes hard to transverse in the direction, go in the direction of normal to sigma. All distance become larger in that direction. But outside, so I do this in a originally small tubular neighborhood of sigma. But outside of that original small neighborhood, which is no longer small after this change, outside of that, I pinch everything almost to something, I scale down the metric so it becomes negligible. Uh, it happens. So if I do this everywhere in a consistent way, it happens that this gives an example. This gives this most counterintuitive counterexample, which is stated in pink. So yeah, let me just say two words why this is a counterexample. So it can be shown that each vertical slice, each vertical three-dimensional cube with this new metric, it has small to width. Why? Because each purple surface was approximately one-dimensional, and you can convince yourself that each free cube can be now mapped to a cone over sigma with small fibers. So this explains why the three cubes have small width, small to width. And another part is to show that the whole, when we assemble all those modified three cubes all together to get a four cube, this has three width large. Okay, so in order to see this, I encourage you to think about all those sigmas in all those cubes. Remember that if you would just take just those sigmas everywhere and glue them together, we'll get a three cube, normal three cube. Of the same approximately metric size that it was at the beginning, but we also did this blow up in the normal direction. So we'll have intuitively we'll have this normal three cube, but also its neighborhood was blown up in the normal direction. So it will have large three width. So that's my attempt to sketch this example. And it happens that this can be done in a greater generality I formulated it just a special case of the general theorem. But this is our best manifestation of how the width fails to measure the deficit of d-dimensionality. So you have a space of dimension approximately 3m. You map it, drop in the dimension to m. So you expect fibers to be approximately 2m dimensional, but they have there happen to be approximately m plus 1 dimensional or something like that. And all fibers also topologically trivial. So yeah. The summary, which I don't have time for, of all those simple examples that I explained. So this is just a collection of all results that I explained. And they don't cover everything. They don't cover all instances of the prototype problem, but they still give some good intuition how hard this question turned out to be. I don't have anything else. I'm gonna thank you for your attention, but maybe I'll just keep this slide with a summary